Welcome back to the last part of our second lecture on Introduction to Complex and Algebraic Geometry. So we continue with the discussion of the equivalence between holomorphic and analytic functions. Let's do a quick review of what we discussed earlier. So we were discussing functions like f, which they were defined on subsets of complex numbers to complex numbers. We defined what is complex derivative of a function. So we learned we say f is complex differentiable at a point z if this limit exists. If the limit that defines derivative, which is limit of f of z plus h minus f of z over h when h goes to 0, if this limit exists, no matter how h goes to 0, right? We defined what does it mean for f to be holomorphic. We said f is holomorphic if we essentially, in a compact way, we have derivative of f with respect to z bar vanishes, right? And we said f is analytic if at any point z naught in its domain, there is a small neighborhood around that. So for any point z there, f can be expressed as an infinite sum, an z minus z naught to the n, where n, the sum goes from n equals 0 to infinity, right? So we learned these three definitions, and the main thing was that these three things are essentially equivalent. So we claimed f being complex differentiable, f being holomorphic, f being analytic, they're all essentially the same thing. So that was the claim. We proved this, that being complex differentiable and holomorphic are the same. We used the Cauchy's integral formula to show analytic implies holomorphic. We still have not proved that holomorphic implies analytic. Note that if we prove holomorphic and analytic are essentially equivalent, then we have completed this picture. So this is the only remaining part, and this is what we want to do now. We want to show if a function f is holomorphic, then it has to be analytic. Okay. So let's write it, theorem. Suppose we have a function f defined on some open subset of C, can be the whole C, suppose is holomorphic. So it satisfies in particular the Cauchy-Riemann equations. Then f is analytic. What should be the idea of the proof? We know derivative of f with respect to z bar is equal to 0. How is that connected to the fact that f of z should be written as an infinite sum? How these two concepts are related? So in order to prove analytic implies holomorphic, we use the Cauchy's integral formula. But the point is that for the converse, for showing holomorphic implies analytic, again, the main ingredient is Cauchy's integral formula. So it's good to think about it. It's good to think why that would make sense. Why should we guess Cauchy's integral formula is useful to prove holomorphic implies analytic? It tells us that if we have a point z naught, if we look at a small disk centered at z naught with radius epsilon so that it falls inside the domain of the holomorphic function, then f of z for any point z inside this disk, f of z is equal to this integral, 1 over 2 pi I, integral of f of w minus z dw over the boundary of this disk. Remember, there was another term, but for holomorphic functions, that other term disappears. So we know f is holomorphic, so that's the whole Cauchy's integral formula for f. There is no second integral. This is the Cauchy's integral formula for holomorphic functions. So why should this be useful? We want from this to get f of z can be written as infinite sum of something. So you might guess Cauchy's integral formula is the way to do it because integral and infinite sum from calculus, you might know, they're closely related. So you might say, well, if I write f as an integral, then there might be a way to do some algebraic manipulations and write the integral as an infinite sum. So it kind of makes sense to use integral. So Cauchy's integral formula should be useful. But actually, that is not the reason. This is not this integral. In fact, the integral there is not really related to this infinite sum. So that's not it. The reason Cauchy's integral formula is the main ingredient to prove this equivalence is not that. It's a slightly different thing. It's in fact related to this quotient, denominator w minus c. It's related to a kernel. A simple way to say it is the following. You might have seen this simple expression, 1 over 1 minus x is equal to sigma x to the n, where n goes from 0 to infinity, when has norm less than 1. You might have seen this in calculus. I leave this to you, but this is a valid expression, even if x is a complex number with norm less than 1. Doesn't have to be real. That's essentially why Cauchy's integral formula is useful. So let me show you. So this is how the proof goes. So proof. So we are assuming, so our assumption, just to be careful what we are doing, our assumption is that f is holomorphic. What we want to prove is that f has a power series expansion, right? Since f is holomorphic, Cauchy's integral formula told us f of z is equal to 1 over 2 pi I integral over the boundary of disk. I don't write the details, f of w over w minus z d of w. This is what we know, right? From this, I want to get f has power series expansion. So look at the denominator. It's 1 over w minus z, just this part. Just this part. Ignore the rest for a second. I can rewrite this part as w minus z naught minus z minus z naught, right? If I do this, plus z naught and minus z naught cancel each other. So these two things are equal, right? And then I can factor out w minus z naught. So I can write this as 1 over w minus z naught times something. So what that something would be, it would be 1 minus z minus z naught over w minus z naught. Okay, let's call this whole thing A. Look at this second expression. Here we have 1 over 1 minus a. So the claim is that we can say 1 over 1 minus a is sigma a to the n, where n goes from 0 to infinity. Why is that? So this is correct. Remember, when a has norm less than 1. So in order to say I can do that, I should say this expression is less than 1, has norm less than 1. But this is true because z naught was the center of the disk. Z was a point inside the disk. W, the variable of integral, is a point on the boundary of the disk. So Z is closer to Z naught compared to W to Z naught. So the distance between Z and Z naught is less than the distance between W minus Z naught. So Z minus Z naught has a smaller norm than W minus Z naught. So their ratio is less than 1. So I can replace this part, 1 over 1 minus a, with sigma a to the n. Therefore, 1 over w minus z is equal to 1 over w minus z naught. I keep that part. Instead of 1 over 1 minus a, I write sigma a to the n, where n goes from 0 to infinity. But here a is z minus z naught over w minus z naught to the n. Now, let's take this back and substitute it into the integral, right? This is this part. Substitute this new thing inside that. So from this, we get f of z is equal to 1 over 2 pi I integral over the boundary of disk, f of w times 1 over w minus z. But instead of that, we learned we have this expression. 1 over w minus z naught times sigma z minus z naught to the n, w minus z naught to the n, where n goes from 0 to infinity, dw. So we just substituted what we had into our integral. And we can just simplify this a bit. So we have the integral f of w, and then we have sigma z minus z naught to the n. And then here we have w minus z naught to the n, but then there's another factor in the denominator, so it would be n plus 1. That n goes from 0 to infinity, right? So Cauchy's integral formula plus this simple thing that 1 over 1 minus a equals sigma a to the n when a is small gives us this. Okay, so why does it tell us that f can be written as sigma n from 0 to infinity some constant times z minus z naught to the n? Well, look at the formula we have. If we have a constant, let's bring that constant here. This sum, infinite sum, is in the variable, the kind of numerator is n. The integral is over w. You can swap them. They have nothing to do with each other. So I can bring sigma out of integral. So I would have sigma and then integral. And what is integral over? There is f of w. And then this is what w is what we are taking integral over, w minus z naught dw. And this z minus z naught to the n, it doesn't have w, the variable of the integral. So we can just bring that out of integral. So look at this whole thing. This is a constant. We are integrating something. The result would be a number, a complex number. Whatever that number is, I just define that to be an. So if I do so, one should just check this is a finite number, and this follows essentially from Cauchy's integral formula, but let's ignore that for a second. If we do so, we get sigma n from 0 to infinity, this integral, which is a number an, times z minus z naught to the n. Therefore, f of z is equal to this infinite sum when z is sufficiently close to z naught. This is exactly what we wanted. F is analytic, right? Because it has this power series expansion. So holomorphic implied analytic. So let's go back to our picture. We had complex differentiable. We learned complex differentiable is the same as holomorphic. Now we proved holomorphic implies analytic. In the previous part, we proved analytic also implies holomorphic. So using Cauchy's integral formula. Therefore, analytic is same as being complex differentiable, right? So the only part which we didn't completely prove is Cauchy's integral formula, and that follows from Stokes' theorem, and that's what we are going to prove in the next lecture. So this is our big picture of being complex differentiable is the same as holomorphic, is the same as analytic. Okay, this is a good place to stop this lecture.